All right, this is Mr. Anderson from Kellogg Community College for statistics. Today what we're going to do is we're going to look at regression lines, or lines of best fit, for looking at scatter plots. Now the first thing we're going to do here is we're going to take a look at some fictitious data about hours worked per week and their respective math grade. Now from the last section we learned about inverse and direct correlation. A direct correlation would be as if one item goes up, the other guy's item goes up as well, so that's a direct correlation. And an indirect or inverse correlation is where if one goes up, like on the x-axis, the other goes down, like on the y-axis. And we can see that by plotting points. Now, one important thing that we need to do here is we need to plot our points and label our x and y axis. So at the bottom here, the x and y axis is determined by the table. And it's pretty standard that the x will be the first row and y will be the second row. But remembering our vocabulary a little bit, the y is the dependent variable, which means the y depends on the x, or the independent variable. So you can change the number of hours of work per week independently, and that will make your dependent variable, the grade, act accordingly. So if you take a look at the independent variable, looks like our range is between 0 and 10, and luckily this goes up to 10, so a scale of 1 would be appropriate. Even though I'm not actually labeling each tick mark there, this is actually a scale of 1. So this x-axis is going to be your homework in terms of hours per week. Homework hours per week. Sorry that this is a little bit crammed on the screen there, but trying to get everything in before scrolling to lose it. Now the math grade percentages, that's going to be on the y-axis, and in terms of your range, it looks like we have a low score of 20 and a high score of 100. Since there's 10 tick marks here on the side, starting at 0 on both x and y and going by 10% on the y-axis would be a fair scale. So our y scale is going to be 10. Okay, and now we get to plot the points. Now what we're going to do is we're going to move over on the x and then up on the y. So for 7 hours of homework per week, this student, this data plot, received an 85%. So there's a dot there. And for the next data plot, which is 5, 60, 5 hours of homework to 60 there. And what I will do is quickly kind of fill these in. And on the homework, I do get some questions about what is adequate for a stem and leaf plot, and what's adequate is that you would have your axis, or both axes labeled, and also have your plot your dots individually. Take a little bit of time. A little bit of time on the homework is going to make me feel like you put your effort into it. And it is a little time consuming, but it isn't that bad. Almost done here. And all right. So the first question is, it says draw a line through the data that you think models the relation between homework and grades the best. So looking at this data, it's not perfectly in a row, so we're not going to have like a 1.00 or a negative 1.00 correlation coefficient. But it does look pretty positive. You see how the dots are kind of moving from left to right in that upwards order. So you're going to take your line and draw it approximately through these dots. Now remember, this is an estimate of the line that you will get on your calculator, but this is, pretty close. Now it says based on the dots, make an estimate of the correlation. Now this is also a guess. Remember that a perfect row of dots would be a positive 1.00 correlation. So this is going to be maybe 0.90. And what we're going to use is our graphing calculator to find our A, B, and our Y prime, which is going to be our line of best fit. Now I'm going to bring up the calculator, which is going to erase everything I did here, but the calculator is going to show us everything and more. And I'd kind of like you to try to be able to do all of this on the graphing calculator. And what I've done is I've actually typed in my list 1 and list 2 information already. To do that, you would have to hit the stat key, then the enter key, and that's where you would get those two lists. Now, to do that, to get your R value, the actual R, A, B, and Y prime values, you would have to go stat, right, 8, enter. Now, this also is a calculator that has its diagnostics turned on. If you don't see your R squared, which is your variance, or your R squared, sorry, that's not variance, scratch that. If you don't see your R squared or your correlation coefficient R, you'll need to hit the second key, the catalog key, scroll down quite a bit until you get to diagnostics on, and you'll have to click that enter, and that will get these R squared and R values up and running. But let me get all this back again. Whoops. Oh shoot, hold on. I'll just go stat right 8, enter, and there we go. Bloop. Alright, so now my estimate of 90% was pretty close. This is a positive correlation of 91%, or 0.91. Now my A value is 5.73. and my B value is 9.10. Now what that is an actual slope. This 5.73 is the starting place on this y-axis, and the B is the slope of that line going up almost a full tick box each time. So it creates this kind of diagonal line. Now, since the software that I'm using eliminates the dots when I move from place to place, what I'm going to do is I am going to write this into my y equals and show this to you on the screen. Now, let's get back to this mode again. My A was 5.74. And if you use your rounding rules here, you can go 5.8 because it's one beyond the whole numbers that we had in our data set. And then we have our slope of 9.1. So let's go and type that in. 5.8 plus 9.1. X, we need an X there because according to what we just did, it's start plus slope x, not your typical y equals mx plus b. And then what I can do is I can go to my y equals. If I have my plot 1 turned on, which it might be from the last worksheet that you did, if not, just make sure it's not, not highlighted. Make sure you highlight it. Then we got to fix our window, and our window goes from 0 through 100 on my x. 0 through 10 on my x. I was thinking the y for a moment, by ones. And my y minimum goes 0 through 100 by tens. Don't change the last number. Now you see we have not only our dots that you plotted on the screen, but you also have that line of best fit, which would probably match what you drew. Now, one little thing about these dots, do you notice how they're kind of crammed in the corner? It might be a good idea when doing a window to maybe go 1 unit beyond your highest data point, even though it doesn't end in 10 and this one goes to 110. But what that does is when you see the picture again, you'll notice that you get to see those data points just a little bit better. For the face-to-face classes, I'll want to see this on your calculators for one of your test questions, so make sure you can do that. Now, what you'll do, and if I go to the screen draw here, it freezes the calc in place, and I can type in, or I can write down that my A value, my slope, was, short-term memory, 5.4? I think it's 5.4, and then this was 9.1. I couldn't quite remember. So this is 5.4 plus 9.1x, and this y prime is my linear regression line that shows up right there on the calculator. Alright, so that's pretty nice. Alright, now, there are some things that we're going to do down below here, but let me kind of move everything down here. It says, okay, show the scatter plot to the teacher. Alright, and so that would get a little check by me on the day of the test. Whoops, little check in the box there. Bloop. Now, the R value. Now here's the thing, we had an R value of 0.913, and that 0.913, I think that 0.913, I mean, that is a really strong positive correlation. And that strong positive correlation, you should look at page 793 at table I, and according to the two-tail test here, we're going to go n-2. We had 11 degrees of freedom because we had 13 data points. According to that table on 793, any positive correlation above 0.553 would be considered enough for us to actually run the problem. And since we had something much greater than that, 0.913, then ta-da, we have it. Now, To do a two-tailed test where we assume that the null hypothesis is that, well, there's no correlation, and our alternative hypothesis is that there is a correlation, we're going to take a t-test for this. And for our null hypothesis is where we take rho equal to 0, and there is a correlation. This is where rho is not equal to 0. And rho is another letter for r. Now, obviously, our rho is like 0.913. So if we do this two-tailed test using our t-values, this is going to show up extremely strong. So let's go and just run that out. All right, so using the t-test table, and this table I think is table F, this is going to give us critical values plus or minus 2.201 with an alpha of 0.5. Now, the t-test is going to be the formula r times the square root of n minus 2, which is 13 minus 2, 11, over 1 minus, in parentheses, r squared. And make sure you put that in parentheses if you give a negative r value. So this is going to be 0.913 times the square root of 11 divided by 1 minus, in parentheses, 0.913 quantity squared. All right, if you compute this out, this gives us 7.42, which is way the heck bigger than 2.201. So our conclusion is that we're going to reject the null hypothesis. We're going to reject the idea that there isn't a correlation. There's a strong correlation, and the t-test backs that up. All right, now the second page. All right, if we go to the second page, we've got another set of data. And instead of me plotting the scatter plot, because I think you can pretty much do that, if you take a look at hours of TV per week in math grade, let me go get my graphing calculator here and show you the results for this one here. Now, I did take my data, I plugged that into list 4 and 5, so I can just quickly grab that data from inside my calculator. Okay, and the scatter plot still should show well, but I've got a brand new R value, and I also have a brand new A and B. My R value is going to be really, really strong. It looks like it's 73%. Oh, sorry, I was looking at the R squared, sorry. My R correlation coefficient is negative 86%. This is a negative correlation. As the hours of TV go up, your math grade goes down. So this is going to be dots that go in a downward pattern, and it has a negative correlation. So you may want to you may want to fill the scatter plot out and do A and B before I show you the final answer for C. So let's go and take a look at the y equals then. So I'm going to type in my formula here. I'm going to type in my A value was 99.45, so 99.5. I'm going to subtract 9.65 or 9.7x, and then here's my graph. And you can see that line of best fit matches a lot of my screen there. So what you would do, and I was a little bit better about remembering this than I was on the previous page. I think I wrote the wrong A value down on the previous page. This is going to be 99.5, and my B is negative 9.65. So it starts here at 99 and goes down about 10 every click, so almost a 45-degree line. And so my line of best fit is 99.5 minus 9.65x. All right. And the R value we found was negative 0.86, about negative 86%, which is a very strong correlation. Remember, according to Table I, a positive or negative 5.33 would be considered strong, and since negative 86% is further away, or actually closer to negative 1 than negative 53%, this is a strong correlation. All right, let me go back to my draw here. Scooting down to the bottom. Okay, so if you're in the face-to-face class or taking the test in the class, you'll have to show that to me. I really expect you to take, in lieu of doing the A and the B and the R by hand, I expect you to be able to do this on the graphing calculator. What does the R value tell you? This is a strongly negative correlation right there. Now, according to our degrees of freedom, our critical values is still going to be the same, plus or minus, sorry that came out a little weird, plus or minus 2.201. All right, so that means what we have here is we have to either we're going to either accept or reject the null hypothesis. The null hypothesis is going to be that there is no correlation, so rho is going to be equal to 0. And yeah, we found out this is like negative 86%, so we know that this is far away from 0, but still kind of roll with me here a little bit in case we never found our R value. Or we're going to say our alternative hypothesis is going to be rho is not equal to 0. Alright, so according to my T equation, and this is very important that you have your negatives exactly in the right spaces, because now I use 3 values for this problem instead of 2, so my answers might be a little different but not too far off. When you do your R squared, you gotta make sure that this is in parentheses. If it's not in parentheses, you'll get a different answer. Your T value should be negative 5.54, or close to that if you round it to 2 decimals. And therefore, according to our two-tailed test, which was plus or minus 2.201, there's my negative. Wow, that's a very bad negative there. There we go. Sharpen that up. 2.201. Check this out. See, we are definitely inside the critical region at negative 5.54. We are going to reject the null hypothesis. Bye-bye, null hypothesis. There is definitely a correlation here. And my handwriting's pretty awesome. You should see me at Draw Something. I'm pretty amazing. Probably would help if I actually had an iPad versus an iPod Touch. Okay. The next piece of the puzzle is to talk about section 10.3, the coefficient of determination, and the standard error of the estimate. So this side of the worksheet is going to be talking about the coefficient of determination. So what is the coefficient of determination? Well, it was that thing that I accidentally called variance on the first page. It's not. The coefficient of determination is R squared. It's the correlation coefficient of correlation. It's that squared. So what this is, it takes our explained variation and divides it by the total variation. So explained variation divided by total variation. So what does this all mean, though? Now, there's a lot of writing, so I'll try to be good in my handwriting. It's the measure of the variation of the dependent variable that is explained AIN by the independent variable. The coefficient of determination is the measure of the variation of the dependent variable that's explained by the independent variable. That right there may not actually sink in too well, because what I'm telling you is that we can kind of account for some of the error based on the independent variable, but sometimes the rest of it is by chance. So if you have a strong correlation of 90%, think back to the first page of our worksheet here, then our R squared is 81. Now what does that mean? Well, according to the definition, let me plug it in and show you why it's a little murky here. This number is a percentage, and it says 81% of the measure of the variation of the dependent variable, it can be explained by the independent variable. Now, that doesn't make any sense, but let me kind of give you a little translation here. 81% can be explained by the independent variable. Now, what's important about that is that when you have a 90% correlation, you can say, okay, 81% of those math grade, 81% can be explained by the homework going into those math grades, but 19% is unexplained. That means that even with a strong correlation of 90% to homework and math grade, you can really only say 81% is really for homework and 19% might be something else. Really smart person, some lurking variables that we can't understand. And what's really amazing about that is when you drop just from 90% to 80% positive correlation, look how this changes. I mean, it's kind of sad, actually, because you go from 90% to 80%, and when you hit 80%, you'll notice that this is, when you square 0.80, you get 0.64, because that's what you're doing, is you're just taking this 0.80 and multiplying it by itself or squaring it. And that means that 80% can be explained by your, let me make that an X. It can be explained by your independent variable. But, oh, not 80%. Crap. Sorry about that. I was back on the, I was looking at that problem there. This says that 64% can be explained, but 36% is unexplained. So if somebody said, hey, I did a survey and I noticed that people who did, this much television and got this smarter, like maybe a baby Einstein thing, which is actually kind of fun if you look that up about the baby Einstein data. But if you say, look, I have this data that says that 80%, there's an 80% correlation between this TV show and intelligence, then you have to say, okay, yeah, but 64% can be explained by the TV show, 36% cannot. Now, when you get beyond 90%, you'll notice that this coefficient of determination gets a lot better. So if I take my 0.95 and square it, what I then get is 0.9025, which means that 90% can now be explained by whatever thing you were doing. Was it a drug that had a 95% correlation? Well, great. 90% of it is because of the drug, and 10% is unexplained, which is kind of scary if you think about the idea that we may never ever get a positive, an R value of 100%. So there's always going to be some unexplained lurking variables, especially when we talk about human behavior and the way people think and stuff. So psychologists and pollsters and business people, you got your work cut out for you. All right. Now, we are finally here at the end here, which is the standard error of the estimate. And this is kind of a neat little trick, because let me show you what this does. The standard error of the estimate, what that does is, or what is that, actually was the standard error of the estimate, it's the standard deviation of the observed Y values about the line of best fit, or the predicted Y prime values. So what this does is it gets the standard deviation around that line of best fit that you found. So what's going to happen here is I'm going to type these into my list 1 and list 2 and then do something new called the Lin regression t-test. And we'll assume the two-tail, and we'll get, instead of doing the standard error of the estimate by hand, we are going to let the graphing calculator do that for us. So back to screen draw here. Let's get my graphing calculator. Now it's unfortunate that I have deleted over that information, but what I can do is clear out my list 1, list 2 by going to the top and going clear enter. Whoops, going to the very top and hitting clear enter, and then type in my data. So let me get the data from the chart here. And then go to my list 2 and put my Y values in. Now we're not going to be graphing this information, we're just going to be using the calculator to find the standard error of the estimate. And let me go through the directions. So I've entered the data, and now I'm going to go to the linear regression t-test. Now I will be writing all this down here, so if you're, you can pause and rewind this video as much as you want, but here are the new commands. You're going to hit stat. Now to get to the linreg t-test, you're going to go 2 clicks over, and then you're going to go down to linear regression t-test, which it's different on different calculators here. I've even found that sometimes it's E, sometimes it's F, but it just depends on which calculator you have. And here it is, linreg t-test. Hit the enter key. Now we want list 1, list 2, where our data is, the frequency 1, and we want this to stay highlighted, which is not equal to 0. And this is where you could type in, like you get the Y1 input command, so it could get plugged into this Y1 space, but we're just going to calculate it because we just need the answers here. Okay, so here's what we have. I like to kind of scroll down a little bit here because I want to be able to see all the things I need. I need my you see my degrees of freedom is 4 and minus 2. There's my slope, there's my start, there's my y-intercept. Now S, that is my standard error of the estimate. And then here's my R and my R squared for my correlation coefficient, which is really strong. And then our, want to make sure I'm not saying the same thing twice, our coefficient of determination. Alright, so here we go. I'm going to now pause this and get back to my drawing tool, which will lock the calculator in place. My A value, which is now off the screen, was 0.396. My B value was 0.106. And my Y prime, sorry that got a little taken off there, is the start plus the slope x. Now, my correlation coefficient was really strong. My coefficient of determination is also really strong, and because you can just square your 0.98 and get you this. Now, here's my standard error of the estimate, which is 0.447. Now, be aware that this is this problem right here. We're talking about your item was 0.447 away from your line. So even though your line, you notice that this line is moving in these decimals, but in the context of the problem, the Y values are in billions of dollars. So this is 396 million and this is 106 million. It says basically for every tens of thousands of cars, you would increase by 106 million. So there's about $500 million of variation between each of your points, according to the standard error of the estimate. So the standard deviation away from this line is $500 million, because one hole here in revenue is in billions of dollars. So it shows you that even though you have such high correlation, your standard deviation could still be pretty far off when you're talking about money like that. Now obviously 0.5 is not a huge standard deviation, but when you talk about your Y value being in billions of dollars, $7 billion, $3.9 billion, that's a lot of money. So let's just talk again about the coefficient of determination. 96% is explained by how many cars you've brought onto your parking lot, but 4% is unexplained. Now, it says right down here, what is the standard error? And instead of moving this all and losing this all, I'm just going to answer this question right over here. What does the standard error of the estimate tell you about the data? The deviation. I'm going to make that look like a V. Hold on. The deviation was 0.447 or $447 million away from the line. And that right there makes you feel good about, like, wow, we had such a positive, strong correlation, but our standard deviation, it still has a lot of wiggle room right there. But it just goes to show you that statistics, although as powerful as it is, can still have a lot of flux in it. And that's maybe why we can't predict the weather to 100% accuracy. The stock market, yeah, I mean, predicting that would make you a millionaire, billionaire. But again, statistics are great, but statistics is great, but man, you can see all of the flux that we can have just in one little problem.